X. Okay, so here's the plan for the day. Here's kind of what we're going to do so you can know what the plan is, know what you're trying to come out of this little instructional experience with. We're going to look at how to come up with some shortcuts for doing differentiation. Okay, this is good. This calculus is full of really good shortcuts. Let's start off. Let's do a little bit of review of how we're, at this point, like on the 2.1 assignments, you're taking derivatives by using these limits, right? So let's kind of review what our approach is, and then we'll see if we can generalize this and come up with some formulas that we can apply in the future that won't force us to always go back and do this limit stuff. Okay, first things first though, I told you the other day that there were some different notations for derivatives, and we've been using this one, right? We say that if f of x is the function, then its derivative we call f prime of x. Okay, and that's very standard. There are some other ones too. Here's one. If we've got some function, say y equals f of x, well, sometimes we'll do things like this. We'll use that notation. That says the derivative with respect to x. And all that really means is just that, for now at least, we'll get into this in more detail in the coming weeks, but for now, this just means derivative, and oftentimes we call this the variable of differentiation. It's just the independent variable, right? It's whatever we're, for us now. Later on, in future years in calculus, you're going to do derivatives with respect to other variables too. This is really derivative or calculus of a single variable this year. You'll move on and do multivariable calculus later, and when you do that, you can apply the concepts of calculus that we're going to talk about to things like surfaces and volumes, and that's where it really gets even more interesting. But this is kind of this is foundationally, it's all the same. Once you know this, that's an easy step. So here's another notation. Derivative with respect to x of something. Usually we'll just make that a y. dy dx is the other, these are the two most common ways that we write derivatives. But you could say things like the derivative with respect to x of some function, like x squared. And that just means we're going to take the derivative of this, and what do we get when we differentiate? There's some textbooks use some other kind of bizarre ones. That's most of them. Oh yeah, this is always a weird one. I don't think I've ever even seen this in a textbook that I've used, but sometimes they'll say stuff like that. Weird stuff like that. Yeah, where that's the variable of differentiation. So there's some weird. And so you may in some point in your future math careers, you may get into a calculus book that uses some different notation. But for the most part, this covers it. Okay. And I'll just try to use them all, so you get used to all of them. So what about this guy here? So if f of x equals x squared, better yet, let's say y equals x squared. What's our derivative? How are we going to do that? We're going to set up dy dx. What's our limit definition of a derivative? In terms of, remember what we said, we took a limit of the function. This is based on that picture. Morphing the secant line, the slope of the secant line, into the slope of the tangent line. Limit of f of x plus delta x minus f of x. F of x. And really that's a change in y, isn't it? Right? Change in y over change in x as good. Okay. So we always start there every time. That never changes till today, till we learn our formula, our shortcut formula. What's that going to be for us, for our specific function? If we've got f of x equals x squared, what's f of x plus delta x? X plus delta x squared. Right, so that's what we get from that guy.
Oh,
Minus
x squared.
x squared. Right? And then we just do algebra. We just gotta get this thing, remove the indeterminacy by canceling some factors. And I think we did one either very much like this or it might have even been this one. What do we do?
We distributed the square to the x.
Okay, good. We expand, the way we say that, we expanded this binomial. We expanded this factor, right? Okay. So we get the limit of, what's that gonna be, x squared
Plus 2x.
plus 2 delta x, plus 2x delta x.
Wait, how do you
If I just FOIL that out, x plus delta x times x plus delta x, I would get x squared plus 2x delta x, thank you, plus delta x squared, right? Plus delta x squared minus x squared all over delta x, and what happens there? On the top?
The x squares cancel.
Good. Okay, we can cancel horizontally, the x squareds cancel. Those are the two naked terms, the ones that don't have delta x's in them. And then we can factor out a delta x and cancel, right? And that's kind of the way it typically works out. So if I factor out a delta x, I'm left with what from these two terms? 2x plus delta x over delta x. And now we can cancel vertically like we needed to.
Yeah.
And that removes that 0 over 0 indeterminacy. We can take the limit. As delta x goes to 0, we're just left with that one term, and that's our answer. That's the derivative function, right? Okay, so let's see if we can generalize this. So we could do lots of these specific ones, but it's always a great strategy in math if we can come up with some general approach that'll work in all cases. So let's take the function, we'll just deal with power functions for now. We'll just take f of x equals x to the n, okay? But n, we're not gonna pin it down. N could be anything, right? And see if we can come up with a formula for that. So we start at the same place we always do, right? If that's f of x, f prime of x, once again, is the limit of
X plus
Delta
x.
x.
That's good, f of x plus delta x. Okay, so that's easy. F of x is just x to the n. What's x plus delta x? F of x plus delta x. Okay, that quantity to the nth power. So okay, and so the tricky part of this comes from right here, right? Whoops. What are we going to do with that? X plus delta x to the n. How can we expand something when we don't even know the power to which we're taking that binomial? Because we're going to get different answers, aren't we? If that's a 2 versus a 3 versus a 4, we're going to get different answers. But can we make some kind of general statement about this? This is kind of a cool proof, or a cool process here, because you can just, you can see that, well, I don't want to spoil it for you. Let's see what happens. So what is x plus delta x to the n? If I were to, let's go back and appeal to that Pascal's triangle we were looking at the other day, and just see if we can see some patterns. So, remember how that went?
Yes.
We just had ones on the outside, right? And then what did we do? Okay, so we added them. So then here we get a 2, there we get a 3, there we get a 3, we get a 4, 6, 4. It's going to go one more row. Okay, so now what these mean, right, is that if I were to take, like this first one just tells us that x plus delta x to the 0 is 1, right? This one tells us x plus delta x to the 1 equals 1x plus 1 delta x. Pretty basic there. But now we start getting into a little bit more interesting territory. This tells us we get x squared plus 2x delta x plus 1 delta x squared, right? And then here we get 1, I'll just put the 1x cubed, right, plus 3x squared delta x to the 1 plus 3x delta x squared plus 1 delta x cubed. Okay, we don't need to probably do the whole thing, but are you noticing a pattern? Like if I were to look at the next one, I'd get 1 x to the 4th plus 4 right? Etc., etc. Here I get 1 x to the 5th plus 5 x to the 4th
Delta x.
delta x, right? So do you see any patterns here? Do you see any relationship? And what I'm looking at, the first one's pretty obvious. It's always a 1.
You grew up in so many patterns before you learned that.
What about those? Where are those numbers coming from? Do you see any relationship between those and the row that they sit on? And keep in mind that what this is, like this row right here, is the quantity x plus delta x to the 3. This is equal to x plus delta x to the 4, right? It's the power of the binomial. It's 1, 2, 3, 4, 5, 6. Oops. 4, sorry. 0, 1, 2, 3, 4, 5. What do you notice? What do you notice about that first coefficient?
It's to the power it is.
Yeah, it's the same as the power of the binomial every time, isn't it?
Yes.
Right. And you can honestly, you can sort of, it makes sense when you know, hindsight's 20/20. If you look at that, it really does make sense. If I were to do something like, say, x plus delta x to the 4th, now think what that really means. That just means the product of x plus delta x, x plus delta x, x plus delta x, and x plus delta x. Well, obviously, if I'm going to go through the laborious process of boiling these out, getting a result, expanding that, or distributing that, you know, expanding it, combining like terms, etc., going all the way through, it's going to be a long process. But how am I going to build the highest power of x? Well, by multiplying x's together in each of the 4 products, right? I'm going to get the biggest power of x when I've done all that immense distribution, when I distribute this term to that term and that result to that term and that result to that term. That's going to give me a 1x to the 4th. That's only going to happen once, isn't it? Each of these binomials only has 1x to offer to the product, to each individual product, and so I'm going to get 1x to the 4th term only. Out of all the different permutations, only once do we multiply 4 x's together. Every other product is going to be some combination of x's and delta x's. But even the x, the next highest power of x, how am I going to get that? Well, I could multiply these 3 together first and get my x cubed, and then multiply that result by him, right, to get an x cubed delta x. Or I could have done these 3 together and then multiplied by that one to get an x cubed delta x. How many different ways am I going to be able to get an x cubed delta x? 4, right? Does that make sense? I mean, can you see the pattern there mathematically? Because each of these binomials, one time, could be the sole giver of a delta x into a product, into the overall product. See what I'm saying? So, I mean, it kind of makes sense. You could even sort of finesse, after that it starts to get pretty hard to keep it all straight, but you can kind of finesse your way through it even to that point. But we can see that that definitely is the pattern, right? And it really is, by the way, if we actually use the more mathematical way of doing this, there is a formula for predicting, there it is, for predicting what the coefficients of each term in a binomial are. It's called the binomial expansion. And it just kind of, it just goes on and on and on and looks like this. Well, notice that if we look at the first two terms, we get x to the n, and then sure enough, n times x to the n minus 1 times delta x to the 1, right? So the next highest power of x always has that coefficient of n. After that, it changes. But it turns out, we don't really care about those other ones anyway, and we'll see why in a second. So if we were to, and this is going to sound a little hokey, but what if we were to just kind of, this is going to be, depending on how big n is, this could be an arbitrarily long expansion. I mean, if n were 1,000,000, that's going to have 1,000,001 terms. So that'd take a long time for me to write. Let's not do 1,000,000. Let's just, but let's just say, we're going to leave it arbitrary, but let's just do the first few terms and see if that's enough. If I were to expand this out then, based on what we just saw, we end up with the limit of all this stuff right here is just going to become x squared plus n, right? Because that's the power. Excuse me, x. Strike that. X to the what there? N, not x squared. We did last time. X to the n plus n times x to 1 less than that.
Yeah, oh yeah, I'm seeing it.
Times
Yep, I'm seeing it. Delta.
delta x to the 1.
Yeah.
Right?
Oh yeah.
Plus, and we don't even have to get specific. We have that binomial formula to rely on if we want to. But wouldn't you agree that that's just going to be some number, right?
Yeah.
For now, that's honestly good enough.
Yeah.
Some number times x to what power? What's going to be the next
N minus
lowest
2.
power of x?
N minus 2.
The n minus 2, good. Close. Times delta x to the what?
2.
2. Yeah, because remember, they always have to add up to n, don't they? Right? And that's really key. That's the, where did I put that thing? Right there. Right? Remember that these always, 3 plus 0 is 1, 2 plus 1 is 3, 3 plus 0 is 3, sorry. 1 plus 2 is 3, 3 plus 0 is 3, 4 plus, right, you get the idea. The powers, right, always have to add up to whatever number of n corresponds to that row, right?
Mm-hmm.
Okay?
Totally got it.
So it's going to be delta x squared plus et cetera. We could keep going if we wanted to. Minus x to the n. Okay?
Yeah.
This guy. All over.
Wow.
Now it looks terrible, but watch how easily this cleans up. Does anybody see, if I were to, get rid of the parentheses, which really don't serve any purpose here anyway, is there any horizontal cancellation? The x to the n's. Yeah, the x to the n's cancel, right? That's good. And now all the other terms have factors of delta x in them, right?
Mm-hmm. Yep. Yep, I see it.
So what's my strategy then? Yeah, I can factor out a delta x so I can cancel that with the one on the bottom, right?
Oh yeah.
If I do that, what am I left with on the top? What's this term going to give me? If I undistribute a delta x. Okay, n x to the n minus 1, right? Next term is just going to be some number times what?
X minus 2.
X to the n minus 2 times
Delta X.
delta x to the 1.
Yeah, I'm totally seeing it.
And if I were to keep
Oh, yeah.
going,
Oh yeah.
wouldn't you agree? I'm just going to end up getting something like this then, plus what? Plus some other number, I don't even care what it is, times x to the n minus 3 delta x squared, for on and on and on. But when I take my limit, what's gonna happen to all those terms? Is in the limit that delta x goes to zero,
Yep. Mm-hmm.
they all disappear, right? Okay, because we're gonna be multiplying each of those terms in the limit times zero, so they vanish. We only end up with one term left over.
Yeah.
So those guys cancel. And then when I take my limit, so that goes to zero, that makes that whole term go to zero, that goes to zero, and we just do that all the way down the line. How about that?
Seeing it, oh yeah.
Right? So it really didn't matter. We don't, those numbers, we could determine what they are, but it's not worth the hassle, because they're all gonna have powers of delta x 1 or greater, and therefore all vanish. So what's our formula then? We got an answer. So the derivative of x to the n is n times x to the n minus 1. That's our power rule for differentiation. How about that? Okay, that's a lot easier, isn't it?
Oh
It
yeah.
makes life much simpler. Okay, let's try that. Instead of having to go through that big limit process, we could do big, imagine how hard this would have been if I'd given you this one a few days ago. You would not have been happy if I had said something like differentiate, we'll use the new notation, find the derivative of x to the 7th. Yikes. That would not have been good to have to take x plus delta x to the 7th and expand that whole thing out. Not fun. But what's the answer?
7x and 6.
Yeah.
That's not
And I'm not gonna prove this to you.
Oh,
You know, if we have time at the end of the year, I'll kind of fill in some gaps, and we'll go back and look at some proofs for some of this stuff. But this applies not just to integers. This applies to lots of them. I mean, like, for example, I could say something like, if y equals x to the 13 halves, then what's y prime? There's a notation I forgot to give you. If we put a y prime by it, that also means derivative. What's y prime?
13 times x to 11.
That's it, right?
This guy, I totally got
Okay.
it.
What is, how about if we have y equals, what if I put a number out front? What if I have y equals 2, oops. Two x to the negative 4. What am I gonna get? Good question. What does that 2 do out front?
It just multiplies.
Yeah, it's just a coefficient. So we can
This guy.
just ignore it. We can just take the negative 4 out front and just multiply it by 2. Right? Because the negative 4 was going to be our coefficient. We started off with a 2, so now we end up with negative 8. X to the
negative
fifth.
negative 5. Exactly, because we're subtracting 1. Okay, make sense?
Yes.
Okay, what do we do? Here's another one. What do we do if I have something like f of x equals 3x to the 5th minus 2x squared? Now I want you just to think here about how we did limits, right? When we did limits of sums, didn't we say that we could split the limit of a sum up into the separate limits, the sum of the separate limits, or a difference? And didn't the formula that we produced for, the power rule for derivatives, that all came from limits, right? I mean, it was a product of, product's a bad word, it was born from the whole limit process, right? So what do you think? How do we deal with differentiating a sum or difference of terms? Give you a hint, it's very simple. Say it again? Split them up, yeah. The way we'd say that we just differentiate term by term. So we can just take each of them individually and take a derivative. Okay, that's very handy also. So what's our answer then? This one just gives us, okay, this one gives us,
What is it to the 4th?
that's it.
for the second.
Oh, whoops. What is with me today? Well, what if I'd had a +3 there? What did we say that the derivative of a constant was the other day? Remember we said that a y equals a constant was just a flat line. What's the slope of that? 0. Yeah, good. The derivative of a constant is always 0. So if I had a +3 there,
There's just zero.
the derivative of that is 0. Yeah. Okay.
You're close.
Make sense?
Not really.
Okay, now something that's pretty good stuff, but that's where the good news ends. We're not going to get to this for a while, but if I had something like f of x equals 2x squared times 3x cubed, can I just differentiate the 2x squared separate from the 3x cubed?
Yeah.
No, I can't.
Oh.
That's where the good news is. That's going to rely on a different rule called the product rule, which we'll get to next week. And it's not really a hard one, but it doesn't work that way. It doesn't work that way. It's a little more complicated. Okay, so we added one new rule. Let's look at one more. Let's look at one more, and then we'll see if we can come up with some more shortcuts. We got to extend this to trig functions now. Which one do I want to do in class? There's two possibilities. I want to do cosine. Oh, you sine. So what about this guy? So this will be good practice for us. This will force us to kind of think in terms of trig a little bit. Okay, so how am I going to take a derivative here? So always start where?
The x plus delta x.
Good. Okay, I have to use the limit definition. Go back to the most fundamental definition of a derivative. So we always start same place. Limit of f of x plus delta x minus f of x. Delta x goes to 0. Okay, this is where things get. Now we got to remember some trig identities. And I bet you don't. I mean, everybody forgets the trig identities over the summer. I did too. Just this is one I can kind of reason out because I know. Well, if you know a couple of them, you can fill in the blanks. But to make your life easier, I am going to, at a convenient time here in the next couple of weeks, I'll give you a sheet of just some stuff I want you to memorize. And I hate doing that. Memorization, I will admit, memorization is the absolute lowest form of learning. It's you forget it eventually anyway. And this is not meant to be something that, I don't remember all the state capitals. I knew them at some point, but it's not a big deal. I can just Google it if I need to. And the same thing is true here. But this is just more of when you're actually doing math. There's a little tool bag of stuff that it's handy to not have to go get because it breaks your train of thought. And so this is one of those things. We're gonna there's a handful, a short list of stuff that I am gonna have you memorize just because it makes your life so much easier to do that. So I'll get that to you. I'm not gonna burden you with it right now, but shortly we'll do that in a time when it seems to fit well with what's going on with our calculus stuff. If we plug this in, well, f of x is just sine of x. What's f of x plus delta x?
Sine of x plus delta x.
Okay. Sine of x plus delta x minus
Sine of x.
Sine x.
Oh, you got it.
delta
Yep,
x. As delta x goes to 0, but what the heck is that? Right? Do you remember what the sine of a plus b is? That's not one that we typically remember, but this is one you can kind of, I'll give you a little, at least the way I remember it. Maybe it'll work for you, maybe it won't. I always remember the double angle formulas really well. Those, because you use those a ton. Like, for example, I remember that sine of 2x is what? Do you remember?
2 sine of x.
Yeah, good. It's 2, keep going, sine x, cosine x, right? That's a big, I'm going to put a star next to that one. That's an important one. We use that a ton in math. And then the other one that goes with that are the double angle identities for cosine. Okay, this one is either, remember this one's either cosine squared minus sine squared. Or if I write the cosine squared as a 1 minus sine squared, I could combine those and say 1 minus 2 sine squared if I want to write it all in terms of sine. Or I could write the sine squared as the quantity 1 minus cosine squared and make that 2 cosine squared x minus 1. You know, depending on which one fits the algebra better that I'm doing at the time. But if I know those, and those are good ones to know off the bat, this really helps. Because the sine of 2x is really just the sine of x plus x, right? So if the sine of x plus x ends up giving me 2 sine x cosine x, where that's coming from is just sine x cosine x plus cosine x sine x. If those had been different, if I'd had something like,
Dude, I'm doing everything.
say I'd had something like sine of a plus b. Well, to get that result, if a and b were the same, how would I get this? If I had sine a cosine b plus cosine a sine, wouldn't that work? Right, if the a and the b were both x's, I would just get sine x cosine x plus sine x cosine x. Right? That's how I remember that one, if that makes sense to you. If it does, great. If it doesn't, you know, maybe you have a better way. So if I do that though, if I use that trig identity, then specifically this becomes, this guy in the red would just become sine x cosine delta x plus cosine x sine delta x. Okay, so now, here's where things get, you gotta be creative. This is kind of, there's so much creativity in that. We'll never give Matt credit for that, but there's a lot, you gotta be really creative in doing these kinds of processes. Can you manipulate this in a way so you can somehow take advantage of our 2 trig identities? I'll just write those down up here, you tell me what they are. Remember, we have the limit of, what, sine theta, or actually whatever, over theta, as theta goes to 0 is 1, and the limit of
1 minus cosine theta of theta is 0.
Okay, good. Can I mix and match things in a way that maybe I could get those out of there? Keeping in mind that instead of a theta, what's our limit approaching? The limit of what is approaching 0 for us? Delta x. Okay, so delta x is like, that's the variable of the limit. That's what the limit is tweaking. Is the limit tweaking the x? No. It's not saying anything about x. It's saying something about delta x, right?
Yeah.
So is there any way that I could, do you see this popping out any place, that sine theta over theta thing?
Sine yeah,
Ah,
I'm
okay.
seeing it.
There's one right there, right?
Yeah.
Okay. Okay, so I got that. That's good. I could partition that. I've really got 3 terms here, don't I, with the common denominator? I've got this first term divided by delta x plus the second term divided by delta x plus the third term divided by delta x, right?
Yes.
So what if I break this one off? I get the limit of cosine x times sine delta x over delta x, right?
Mm-hmm.
Okay. So there's that one. What about the other 2? What about the other 2? If I look at the other 2, I just ignore this guy. I've got a sine x cosine delta x minus sine x. That looks a little messy, but it's always helpful if we can try to get things factored. Is there something I could factor out of both of those 2 terms?
Sine x.
A sine x, yeah. Okay, so if I take a sine x out, what's left on the top? Cosine x.
That's 1.
Hey, how about if I do this? Cosine x minus 1. How about if I instead, what if I factor out, just to make things, so I can skip a step, That's not quite gonna match, is it? I wanna have a 1 minus cosine x and not a cosine x minus 1. So what if I factor out a negative sine x? Okay? Everybody with me on that?
Yeah.
Okay, so I'll make that a minus sign. And then I'm left with 1 minus, there you go, cosine for x, good, over delta x, right? And if I take those limits, look what happens. What's this limit equal to? In the limit that delta x goes to 0, 0, isn't it, right? That's just this guy. Our theta is a delta x, and the answer is that limit is 0, right? So this one is going to disappear, so that second term goes away, right? This limit here, okay, yeah, that one just goes to 1, leaving me with the cosine. How about that? So all we're left with, when all the dust settles from that whole process, is just that one little cosine x, right? And I want you to notice something else. This may not seem like a big deal, but I want this to kind of stick with you a little bit. Notice that the x there, it acted not like a variable. It is a variable, clearly, but as far as the limit was concerned, the limit is only acting on the delta x, and so the x's were just left unaffected, right? Eventually, we're going to do calculus using many layers. We'll do things like we'll take limits of sums of, we'll do all kinds of things. We'll use sigma notation. And every time we apply one of those processes, it's only going to act on a certain variable. All the other stuff, it's going to treat as being a constant. And so if this may not make perfect sense right now, but hopefully it'll plant a seed that I think when we talk about it again, you'll say, oh yeah, I kind of remember that. So because this is a delta x, the x's were left alone. The limit was acting on delta x's, so the x's were literally treated like constants as far as the limit is concerned. Now the next layer of the calculus, when we add more layers, maybe it's acting on the x's. But that step didn't. Does that make sense? Yes, sir.
Yeah, I'm sorry, could you briefly go over again, how you got the blue term in the middle, like the whole minus sine x?
Yeah, how did we get that? Okay, so this stuff, here, let me circle some things. So this stuff right here, right, went to there,
Yeah, I got it.
right? And so what we're left with, once we get rid of that guy, we're just left with sine x cosine delta x over delta x minus sine x over delta x, right? Okay, and maybe I should write that down. So we got, I use different color, that's bad color. So we have to use purple. Minus sine x over delta x plus sine x cosine delta x over delta x. Right? Okay, I could factor out a sine x for both of those two terms, leaving me with sine x times what? Well, negative 1 over delta x plus cosine x over the same delta x. So I'll have a common denominator. Does that make sense?
Yep, awesome,
Yeah.
thank you.
Everybody else okay with that? Okay. Okay, and so we got an answer to our original here. So f prime of x was equal to cosine x. We got another rule. Let's summarize those. So far we got 2. Wow, actually we have more than that. What do we know? We know that the derivative with respect to x of a constant is 0. So yeah, we know that. We didn't ever write it down, but we know that one. Sometimes you'll see this in books too. What's the derivative with respect to x of x? We can just use our power rule there. That's x to the 1. So what do we get? 1 x to the 0. So just 1, right? Does that make sense? And then really that's kind of a wasted one because that one really comes from this guy that we just proved. Power rule, right? Where here x was just a 1. What was that one? Good, okay. We could, if we want to, we could go ahead and add a constant there to any of these for that matter. the derivative with respect to x of cx to the n. How's that change it?
CN.
Yeah. Just multiply c times that n. And now we've added a trig one. Derivative with respect to x of sine x equals cosine x. Okay. Now, the proof would be very, very similar, so I'm not gonna do it. But the one that goes with that would be the derivative with respect to x of cosine x. And you'd be tempted to say probably sine x, but you'd be wrong. It's minus sine x. Okay. And we got some. We're gonna add some more soon. Soon. Within a week, we'll add 4 more. We'll add the derivatives of the other trig functions. Okay, and we'll add the product rule and the quotient rule. Okay, so these are what we call the basic differentiation rules. We'll practice these. This is a pretty easy assignment. You guys can practice these a little bit, and then we'll come back and use those to develop some more useful harder situations. Like how do we deal with the derivative of a product of 2 functions? How do we deal with the derivative of a quotient of 2 functions? How do we deal with the derivative of a tangent function? And then, coming down the line in a couple weeks, I just want you to kind of have an appreciation for we're still a little limited. Notice that all these functions we're dealing with are just functions of the variable x. What if I wanted to do a composition of functions? I wanted to say something like, instead of the derivative of sine x, what if I want to do the derivative of sine of something like 3x squared plus x? Without having to do a ton of horrible algebra to expand that whole thing out, there's an easy way to do it. It's called the chain rule. And that's kind of the next few steps we're going to take. Start with what we just learned today and just expand massively without too much effort to give us a lot of power. So, make sense?
Yes.
Okay. How about takes us to the end? Is that enough for one day?
Yeah.
Yeah,
Okay.
my brain's.
So,